I believe that multiplication is one of the things that is taught very inefficiently in a lot of classrooms. It seems like there's a lot of emphasis on multiplication facts, on memorizing, and maybe on rules and procedures, and less emphasis on multiplication and what it means, and also how it relates to other mathematical operations. When students are introduced to multiplication problems, it's very important, as with other math concepts, that they start with real objects. And here you'll see on the slide drawings of things. You see groups of dots, you see a table or an array. But if students have real things in front of them that they can manipulate, stones or counters or anything that they can form into groups, it's much easier for them to understand what multiplication really means. So we always want to start with that first. Once they've worked with manipulatives and they've worked with real objects, then we can move to diagrams or drawings or sketches or other things that represent those real objects. So for example, if we have the problem 3 times 8, what does that mean? It means we have 3 groups of 8. So here you see one group of 8 dots. Here you see a second group of 8 dots. Here you see a third group of 8 dots. And it's very important that students understand that these groups are the same. So 3 times 8 means we have 3 like groups, 3 groups of 8. To find the answer, of course, then they can look at these pictures and diagrams and just count the answers, or some students may add 8 plus 8 plus 8 by looking at the diagram. The same thing can be accomplished by using a table or arrays. So if we have 4 times 6, that means we have 4 groups of 6, or in this case, we have 6 things in a row. 1, 2, 3, 4, 5, 6. So there's our one group of 6, and then we have 4 of those rows. 1, 2, 3, 4. Again, when students see that array or that table, they can find the answer by counting or by adding. They can see that the answer to the problem 4 by 6 is actually 6 plus 6 plus 6 plus 6. As we're teaching students multiplication and what it means with real objects and with diagrams and drawings, we want them to discover that multiplication is commutative. Sometimes when students are doing real-world problems, there could be an actual label with the problem. For example, if every student in the class had 3 pencils and there were 24 students, then we would want to make sure that they understand that the problem is 24 times 3 pencils. But in mathematical situations where there isn't a label, where it doesn't matter really which number represents the group, it's best for them to understand that they can go either way. So for example, the problem 4 times 6 can mean 4 times 6. We're going to take a group of 6 4 times. It can be 4 groups of 6, but it can also be 6 groups of 4. And rather than us telling them this, the best way for them to learn it, I believe, is for them to discover it. So if we have students working in partners, for example, and they're working with counters or stones, and we ask them to show us the problem 4 times 6, we could have one person in the group make 4 groups of 6, and the other person in the group make 6 groups of 4. And if we do this with a few problems, and we have them count up how many they have, they will discover that multiplication is commutative, that it works either way. So in our arrays here, we have 1, 2, 3, 4, 5, 6, and we have 4 groups of 6. And in this array, we have 1, 2, 3, 4, but we have 6 groups of 4, and they can see that they are the same. Arrays are nice this way also because we can tilt and turn, and students can actually see that the answer will be the same. When we get to numbers and we aren't using real objects anymore and we aren't using diagrams, drawings, or arrays anymore, then we need to make sure that students really understand that multiplication is repeated addition. We need to relate those two operations. Sometimes students see multiplication as a brand new thing, something that's challenging and something that they've never done before, when in reality it is something they've done before, it's just a different way to express it. So we want to make sure that students understand that, for example, the problem 3 times 8 means 8 plus 8 plus 8. We're taking 8 3 times. Or the problem 4 times 6 means we're taking the number 6 4 times. 6 plus 6 plus 6 plus 6. It's very important that students can see that relationship between multiplication and addition. And again, we can point out, as we have had them prove with real objects and arrays and drawings, that multiplication is commutative. So 3 times 8 may look like this, but it could also look like this. Or 4 times 6 may look like this, but it can also look like this. The reason we would want them to know that is because sometimes it's easier for students to calculate one way or the other. So rather than adding a smaller number many times, it might be easier for them to add the bigger number fewer times. We want them to have the option. Once we move to 2-digit problems in multiplication, it's often true in schools that we move to simply rules and procedures, that teachers put the problem on the board, they model how to do the problem, how to find the answer, and we lose the meaning. I think at this point it's still very crucial for students to know, what does this problem look like? With bigger numbers, of course, it's a little more difficult. We could have students do a problem or two with real objects just so they can see how complicated it is to count out that many things, which reinforces the idea that multiplication is a shortcut. But it's quite efficient, actually, to use graph paper or a grid of some sort to have students see the meaning of this problem. So for example, if the problem is 14 times 17, that means we have a group of 17 and we're going to take it 14 times. So here we have one row of 17 squares. That's one group of 17. Now if we take that one group of 17 and instead we make 14 groups of 17, then it looks like this, because we have one group of 17 here at the top, and as we go down we're adding more and more groups until finally we have 14 groups, 14 rows of 17 across. So this square represents our answer, and students can look at that square and they could count up every little square in the bigger square to find out what the answer is. Or they could say, okay, well there are 17 in each row and there are 14 rows, so that's 17 plus 17 plus 17 plus 17, and keep going until they add all of the 14 groups of 17. That reinforces the idea again that multiplication truly is a shortcut. At this point we can apply place value. So this diagram is really showing the same thing. We have a row of 17 going this way, and we have 14 groups of that 17 going down. So we have the same thing that we had in the slide before. However, this time we're looking at our numbers with place value. So the number 17 is actually made up of one group of 10, right here, and 7 ones. So we have 7 ones and we have 10. A group of 10 and a group of 7 makes up each row. As we look at our 14 rows, we have one group of 10 and we have 4 ones. So if we look at this, we have 17 across and we have 14 down, just like we had in the previous drawing. But when we separate according to place value, it makes it much easier for us to calculate the answer, to actually see the answer visually. So if this is a 10 by 10 square, because we have 10 across and 10 down, that means that we have 100 small squares here. Here we have 7 across, but we still have 10 down. So in this square, we have 70. Here we still have 10 across, but we have 4 down. So in this square we have 40. And here we have 7 across, and we have 4 down, so we have 28. So if students see this problem this way, it's much faster for them then to add up the answer to see that they have 100 plus 70 plus 40 plus 28, and they can add those together to calculate the answer. It's just an easier way to visualize, using those groups of 10s and 1s, what the answer would be. Once we get to actual procedures in math, there are many ways that we can approach this. And in a minute we'll talk about place value math, we'll talk about how to do the math in the traditional way. One of the ways that's commonly taught in schools now is the lattice method. So for example, with this problem, we have 43 times 25. When we have students create this grid with the diagonals, what it's doing for us is actually helping us with the place value. Now I'm just going to show you how this is done, just procedurally. And the nice thing about this method is that students can really start anywhere. They can multiply in any order as long as they put things in the right places. So I'm going to start by taking this 4 times 2. 4 times 2 is 8. 3 times 2 is 6. 4 times 5 is 20. And 3 times 5 is 15. So what we do now is we add diagonally, and the place value is just automatically done for us. So when we go down this direction, we have 5 ones. When we add down this diagonal, we have 7 tens. When we add down this diagonal, we have 10 hundreds, and here we have 0 thousands. Now we know that 10 hundreds would be the same as 1,000, so we're going to actually move that up here to 1,000, which means we now have no hundreds at all. So our answer is 1,075. What's nice about this method for students is that it helps them to organize. It gets rid of all that carrying and all that trading and all the rows, and it's just easier for students to keep things in place. What we need them to understand as we introduce this is that these diagonal areas really are representing the place value. So here in this column we're taking ones times ones, and here's tens, and here's hundreds, and here's thousands. That's actually much easier to explain in different ways other than lattice. So to me, the biggest benefit of lattice is just helping students who have trouble staying organized be accurate in their work. When we move from visuals to do double-digit multiplication to regular problems with just numbers, we still want students to be able to think about that place value approach. We want them to think about the value of the numbers. And it's always good for them to think about estimating just to begin. So for example, this 4 represents 40 times 20 if we were to estimate. 40 times 20 or 40 times 2 tens would be 80 tens or 800. So that would be a very low estimate, but at least it would give students the idea, a ballpark range that their answers should fit close to. Once we get into the actual multiplication, the nice thing about the place value method is that they can start anywhere and they can do it in any order, but they are thinking about the value of the number. So for example, if I start with the 2 tens here, I'm going to take the 2 tens times the 40. And 2 tens times 40 would be 80 tens, or 800. Then I take the 2 tens times the 3 ones, and I get 6 tens. Now I'm done with the 2, so if I move to the 5, and I take the 5 times the 4 tens, that gives me 20 tens. And if I take the 5 ones times the 3 ones, that gives me 15 ones. And if I add all of those together, I get my answer. When I get here, I have 8 plus 2 in the hundreds column, which is 10 hundreds. So this is good for students also to think about the fact that 10 hundreds is the same as 1,000. So this is my answer. Once we move from all the conceptual things that are so important in multiplication to regular traditional procedures, we still want students to be thinking about the value of what they're doing. So let's look at how we do this problem traditionally. 5 times 3 is 15. 5 times 4 is 20 plus 1 is 21. But that 21 is actually 21 tens. And if we look at where the 21 is being written, that makes sense because we already have a number in the ones place. Now we're done with the 5. We don't have any more ones to multiply, so we put a 0 here because we're not multiplying by ones anymore. Now we're going to be working to the next number. We also want to teach students to get rid of all these numbers up here that they carry, or it can be confusing for them. Now we're looking at the tens place, and we have 2 tens times 3, which is 6 tens, or 60. We have 2 tens times 40, which is 80 tens, or 800. And if we put that 8 there, you can see that we already have numbers in the tens and the ones place, so that 8 really does mean 800. If we add that together, we again have 8 plus 2 hundreds makes 10 hundreds, which is 1,000. So again, even when students are following procedures that are more rules, more rote learning, we still want them to be thinking about the value of the number and whether their work makes sense. Teaching multiplication well is very important. We need to relate it to other math concepts like addition, like division, so that students understand that multiplication and division are inverse operations. And we need to make sure that they understand what multiplication means. And anytime we're not sure of that, we should back up from the procedure to something that's more visual or to something that uses real objects, so that they can explain their thinking so we're sure they really understand the meaning of multiplication.